Hi there, this is Electromagnetism Lesson 1, and we're going to look what a magnetic field is, what direction magnetic fields point. We're going to look at how to plot field lines and the differences between induced and permanent magnets. Remember to pause at any point just to make any notes. Alright, so what is a magnet? A magnet is an object or material that produces a magnetic field. Now magnetic fields, obviously you can't see them. So in this image below, there's a bar magnet, and you can see the north and the south poles. And what's happened is someone's sprinkled iron filings on there. And what they do, the iron filings will arrange themselves and show you the field lines. So that's a magnetic field. Okay, now you probably all know this, but the laws of magnets. So every magnet has a north and south pole. It says, let's see what happens. So if you put two norths together, you probably already know this, but they will repel. The south and the south, so they're the same, so they will repel as well. And opposites attract, so north and south, or south and north, they will attract. So what happens here, question 1 and 2, I'm going to pause and just write down. So the first two will obviously, they're opposites, so they will attract. The bottom two souths together, repulsion. So here's how you could draw a magnetic field in an examination. So one thing that you really need to remember is that magnetic field lines go from north to south. So you can see the arrows in this image on the bottom left. All of the arrows go from north to south. And the field is the strongest at the poles, where the density of field lines is greatest. So there's more, as you can see on both images actually. The north and south poles on the image on the right, higher density of iron filings. And on the image on the left, you've got obviously the lines at the poles are closer together. So basically you might be asked to draw this in an examination, the one on the left. Just make note, obviously I'd get this down, but make note that the arrows come out of the North Pole and go into the South Pole. Okay, let's move on. So I thought you should know this, but a compass. So a compass is a device that contains a small free-moving bar magnet. It's really straightforward. All it does is line up with the field lines, and it always points to magnetic north. There's a slight difference between magnetic north and geographical north. It's out by about 11 degrees, but I'll show you that in an image in a moment. Alright, let's move on. So how can we plot a magnetic field? So, just to consolidate, a magnetic field is a volume of space where you get magnetic forces exerted. All magnets are surrounded by magnetic fields. The shape of it can be shown with iron filings, obviously on this image again, or with plotting compasses. So if you put now plotting compasses are really small, but you might have seen them at school. But if you get these little compasses and line them up, you can see that they all point in the direction of the field lines. Now I might be asked to talk about this on an exam, and basically you just need to say that the compasses got little bar magnets inside, and they point north. And if you put them in this arrangement like this, they will point in the direction of the field lines from north to south. Alright, let's move on. So this is the difference between geographical north and magnetic north that I talked about. So this is just a representation of the Earth's magnetic field. I've not really seen any exam questions at GCSE level that talk about this or ask about this, but you never know, it might, you could get an image of the Earth and it just says, right, plot the magnetic field. So you notice there's a difference between the magnetic poles and the geographic location. And you might also notice that the field lines are actually going from south to north, which might seem a bit strange. I told you that magnetic field lines are always north to south. So the Earth's magnetic field can actually flip. So I've actually read into this a little bit, and on average they might flip locations every a couple 100,000 years. There's been some new analysis that the last time the poles flipped was around 42,000 years ago. There's an interesting article on New Scientist, and there's also some theory that it led to a lot of problems. So if if you're interested in that, I'd advise you look it up, geomagnetic reversal. All right, let's move on. So draw the field. You probably don't have a magnet in your house unless you're super cool. You probably don't even have a compass, but if you do, the compass being the plotting compasses, you probably definitely don't have them actually. However, what you can do is just sketch north to south and practice drawing the magnetic field that we looked at previously, which you probably should have a copy of already. So they come out of north, so I'll attempt to draw this. It won't be very neat, told you. Into south, so I'll just draw 3 there. And then you should have some that go round. So north to south. That's probably enough in your exam. Don't cross the field lines. You might want to draw another one in there. Do not cross field lines. If you cross field lines, you'll lose marks. Something like that, perfectly fine. Just remember north to south. All right, let's move on. So contact forces. So if you've done forces, you should know this, that when a force is applied due to 2 objects touching, we call it a contact force. However, what do you think we call the force between 2 magnets? So obviously if you push 2 south poles or 2 north poles together, there is no contact. So we call it a non-contact force. So magnets apply non-contact forces to each other or to magnetic materials. So it means that they can apply a force without touching each other. You could get asked a simple question to give an example of a contact force and a non-contact force. So a non-contact force, just talk about magnets. Contact force, you could talk about, maybe a reaction force. When if you sat on your chair or stood up, your weight acts through the bed, or your weight acts through the chair, and then the chair or bed or floor or whatever it is push back up against you, and it's a contact force. All right, so the last thing, there's 2 types of magnets that you need to know about: permanent magnets and induced magnets. So permanent magnets a permanent magnet has a magnetic field around it at all times, and it can be attractive or repulsive. Induced magnet is a magnetic material that becomes a magnet when placed within a magnetic field, and induced magnets can only be attractive. You could be asked the differences between permanent and induced magnets. So I'd make sure that I got that down. Next slide, I'm going to give you some examples of induced magnets. All right, so here we go. So aluminium or aluminum, if you're American, stainless steel, copper, iron, nickel, gold, cobalt, and different rare earth metals. So I want to know a few of those. Could ask you some examples of induced magnets. All right, and then lastly, so continuation of induced magnetism. If a magnetic material, so those examples, cobalt, nickel, steel, iron, are placed in a permanent magnetic field, close by, it becomes a magnet itself. So therefore it's an induced magnet. And induced magnets even have a north and south pole orientation. However, the effect is temporary and it disappears once you remove it from the field. And there's a little image below that's quite helpful. So it's just got 2 materials, iron and steel, which are obviously induced magnets. They've been put next to a bar magnet, and this is the orientation in which they line up. Right, I hope you found that introduction to magnetism useful. Thanks for watching.